Thank
So,
you, Dan.
hello everyone. Thanks for joining our North American JMAG User Conference. My name is Brian Kowalczyk. I'm the JMAG coordinator for university support. Today we are privileged to have as our next speaker, Dwipayan Barman. Dwipayan comes to us from Concordia University in Montreal, Canada. He received his bachelor's degree from Jadavpur University, India in 2011, and his master's degree from Indian Institute of Technology, Kharagpur, India in 2013, both in electrical engineering. He was then a research assistant for several years at the Indian Institute of Technology. Currently, he is a PhD candidate in the Department of Electrical and Computer Engineering at Concordia. Today, he will be presenting his work on simulation of a variable flux machine in JMAG. Attendees can enter questions through a Q&A tag at the bottom of the screen. Feel free to do that during the presentation and we'll work to answer those questions. So with that, I would like to welcome Dwipayan. Dwipayan, you can proceed.
Yeah, thank you, Brian. So I am a PhD student. I am myself Dwipayan Barman, and I am a PhD student at Concordia University under the supervision of Professor Pugashan Pillai. And I mainly work on the radial flux machine, variable flux machine, and axial flux machine for electrical vehicle application. Today I am going to present a simulation of a variable flux permanent magnet synchronous machine using JMAG. This is the outline of my presentation. In the introduction part, I will tell briefly about the basic features of the variable flux permanent magnet synchronous machine. Then I will tell about the base characteristics of the alnico-9 magnet, which is used in the variable flux permanent magnet synchronous machine in our case. And later I will discuss about the cocking torque of the variable flux permanent magnet synchronous machine at different magnetization levels. Subsequently, I will analyze the results of back EMF and torque of the variable flux machines which are obtained from JMAG at different magnetization levels. Another issue of the variable flux permanent magnet synchronous machine is demagnetization and magnetization of the alnico-9 magnet, which will be discussed later in detail. And finally, the presentation will be concluded. The variable flux PMSMs use lower coercive force magnets so that we can control the air gap flux density. In our case, we are using alnico-9 magnet because alnico-9 magnet has lower coercive force. Also, some research paper tell it active magnetization technique. We can actively change the magnetization and demagnetization level of the alnico-9 magnet. That is why there is no requirement of additional continuous d-axis current in the extended speed operation, and the efficiency of and torque of the variable flux PMSM in the extended speed operation is higher compared to the rare earth permanent magnet synchronous machine due to the elimination of this continuous additional d-axis negative current. Also, the alnico-9 magnet are less expensive and they are readily available in the market. One section of the variable flux PMSMs which I am working in the peer group is shown in figure 1. The different parts of the variable flux PMSM are shown: rotor core, hub, stator core. Mainly the unique design is the flux barrier. This flux barrier is provided to avoid the demagnetizing field provided by the armature current. The detailed specifications of the variable flux PMSM is shown in table 1. This is a 3-phase 7.5 HP 27 slot 6-pole variable flux PMSM. The air gap of the variable flux PMSM varies 0.4 millimeter in the d-axis to 0.7 millimeter in the q-axis. This variation of the air gap not only improves the TSD of the back EMF, but also it reduces the magnetizing current of the variable flux PMSM, and which consequences reduce inverter rating to drag the variable flux PMSM. But one of the major problem is that the VH characteristic of the alniconide magnet is only available at 100% magnetization. But we have to investigate the performance of the variable flux PMSM at different magnetization level. So in our case, 25, 50, and 75. So to obtain the VH characteristics of the alniconide magnet at those magnetization level, the recoil line at those magnetization level are drawn parallel to the recoil line at 100% magnetization level. Thus, the base characteristics of the alniconide magnet at different magnetization levels shown in figure 2 are obtained. So another problem of the variable flux PMSM is like a rare earth permanent magnet synchronous machine is Cogging torque. Cogging torque is mainly the no load reluctance torque due to the magnetic attraction between the slotted stator and the permanent magnets. Cogging torque mainly contributes to the slot harmonics. In figure 3, we can see as the magnetization level increases, the Cogging torque also increases, because Cogging torque is a function of magnetic flux density, and as the magnetization level increases, flux density in the air gap also increases, and hence the Cogging torque increases with the higher magnetization level, as shown in figure 3. So at 50 and 70 and 100% magnetization level, the back EMF of the variable flux PMSM are obtained using the JMAG software. And we can see as the magnetization level increases, the magnitude of the back EMF also increases. A flux vector plot of the flux density of the variable flux PMSM at 100% magnetization and no load are shown at different parts of the variable flux PMSM, and we can see the flux distribution. First Fourier transform on the back EMF of the variable flux PMSM at different magnetization levels are performed, and we can see that as the magnetization level increases, the fundamental of the back EMF also increases. TSD of the back EMF at different magnetization level are also calculated and shown in figure 6. And as we can see that as the magnetization level decreases, the TSD of the back EMF increases, because as the magnetization level decreases, the fundamental of the back EMF decreases, and hence the TSD of the back EMF increases. Also, regarding the harmonic of the back EMF, the 3rd, 5th, and 7th harmonic, these are the harmonics which are mainly because of the spatial distribution of the flux density. And 17, 19, 35, and 37, these harmonics are created because of the slotting effect of the variable flux PMSM. Also, we can tell these harmonics are because of the Cogging torque. Several techniques can be used to minimize these 17, 19, and 35 and 37 harmonics, like skewing, pole pairing. That is another kind of research area. The torque of the variable flux PMSM at different magnetization level, 50, 75, and 100% are shown. And we can see that as the magnetization level increases, the average torque of the variable flux PMSM also increases. The flux distribution of the variable flux PMSM at 100% magnetization and rated current are shown in different parts of the variable flux PMSM. We can see that in the core of the variable flux PMSM rotor and stator core, the magnitude of the flux density is higher, but in the barrier, which is mainly nothing but air, the magnitude of the flux density is almost zero. Using the results of figure 8 in the earlier slide of torque at different magnetization level, the peak-to-peak torque, average torque, and torque ripple, these parameters are calculated based on those results. Torque ripple is nothing but as a percentage of peak-to-peak torque to average torque over one period of electromagnetic torque. In this table 3, we can see that as the magnetization level increases, the torque ripple of the variable flux PMSM decreases, because we can see that as the peak-to-peak torque is same independent of the magnetization, and but the average torque decreases with lower level of magnetization, and that is why we can see that lower magnetization the torque ripple is higher. Like for 50% magnetization, we can see it is 24.7%, and at 100% it is lower. It is around 13.9%. Another issue of the variable flux PMSM is demagnetization and magnetization of the alnico-9 magnet. To investigate the demagnetization and magnetization of the alnico-9 magnet, 6 probes are placed along the length of the permanent magnet pole as shown in figure 9. And to demagnetize and magnetize the alnico-9 magnet, the current pulse is applied on to the armature winding, which is shown in figure 10. Actually, pulse 1 is required to demagnetize the alnico-9 magnet, and the demagnetized alnico-9 magnet is magnetized again by applying current pulse 2. The magnitude of the magnetizing current pulse is higher compared to the demagnetizing current, as we can see in figure 10. So after the demagnetization and magnetization operation, we can see that after 0.005 second, in figure 11, basically, the magnetic flux density goes to 0, and after 0.015 second, after removing the magnetizing current pulse, the magnetic flux density again goes to 1 Tesla. So we can conclude that the permanent alnico-9 magnet can be demagnetized with a current pulse and magnetized again with another current pulse. And flux distribution of the alnico-9 magnet of the demagnetized permanent magnet pole obtained from the JMAG is shown figure 12, and we can see that the flux density of the alnico-9 magnet is close to 0, and we can conclude from this observation that the alnico-9 magnet can be completely demagnetized. So coming to the conclusion, so we can see that cogging torque increases with higher magnetization level, because cogging torque is a function of magnetic flux density, and as the magnetization level increases, flux density in the air gap increases, and hence the cogging torque increases. The TSD of the back EMF increases as the magnetization level decreases, because the fundamental of the back EMF decreases with lower magnetization level, and hence the TSD also increases. And same for torque ripple. As the average torque of the variable flux PMSM decreases with lower magnetization level, but the peak-to-peak torque is same independent of the magnetization. Hence, the torque ripple increases with lower magnetization level. Also, JMAG results show that the permanent pole, basically a liquid magnet, can be demagnetized and magnetized by applying a current pulse. This is the reference. This is the few papers published from our lab peer group, Concord University. And this research work is done as a part of INSARC or Hydro-Quebec Industrial Research Chair entitled Design and Performance of Special Electrical Machines. The author also acknowledged the support of Natural Sciences and Engineering Research Council of Canada. Thank you. Please, if you have any question, you can ask me. Thank you.
Thanks. Thanks, Dwight-Pan.
Yeah, thank you. I should stop.
No, you could leave your presentation up. We'll see. I'm not seeing any questions yet. I would like to tell the attendees that you can type some questions in for Dwight-Pan. At the bottom of your Zoom screen, there's a Q&A tag. You can hit the tag there.
Yes.
And you can feel free to type questions in. So there is a question that just came in, Dwight-Pan, from Atul. It says, can you mention any mitigation methods to reduce torque ripple or cogging?
Okay, torque ripple and cogging. Okay. So how can I write? I am unable to write. Can
you can, yeah, feel free to answer, or you could type your answer in the Q&A.
I'm unable to. I am unable to.
You can speak, Dwight-Pan. You can just answer.
Yeah, I can answer now. Yeah. Okay, I can speak now.
Yes, you can speak to answer the question.
So in the variable flux PMSM, another we have performed the screwing technique in my case to mitigate the cogging, to minimize the cogging torque and mitigate the torque ripple at different magnetization level. But the problem is, like, you have to choose the minimum optimum screwing angle, because screwing can create non-uniformity in the magnetization and demagnetization level of the variable flux PMSM if the screwing angle is higher. So in my case, I found the minimum optimum screwing angle to minimize the non-uniformity of the screw power magnet. And also some researcher I have seen, they are working on magnetization shaping technique by applying current pulse to mitigate the torque ripple as well as cogging torque. Thank you.
I see there's. Here's a there's another question. I'll read it for you, and then you can answer. So, how to define the magnetization / demagnetization currents levels, which related to each magnetization level? So it's the magnetization demag current levels relating to each magnetization level.
Okay, so like first we analytically design the variable flux PMSM. Then those results are verified by using FEA. In my case, I use JMAG, like to obtain the flux linkage characteristics of the variable flux PMSM from 0 magnetization level to 100% magnetization level. And once we define those characteristics by design or FEA, whatever, then you can decide, okay, for suppose I want to go to from 0 to 100%. From those characteristics, you can understand that this much current pulse, magnitude current pulse is required. Suppose you want to go 50%, then you can accordingly apply a current pulse of proper magnitude from the available characteristics. Yeah, that you can define analytically, as well as we can validate those analytical results first by FEA. And once those are obtained, we can also later verify by experiment. But first we have to obtain those characteristics. Thank you.
That is letting me know, Dwight, there's a question from the Hoover app. It says, how minimum air gap matters on efficiency? How air gap matters on efficiency? Can you speak to that possibly?
Yeah, because if the air gap increases, so suppose my magnet thickness and strength is same. Now, if the air gap increases, so my power factor will go down because if the air gap increases, my reactive power requirement will be higher. So for the same machine and same strength and same dimension of power magnet, the output power of the machine will go down, and as well as so efficiency will decrease, as well as power density will also decrease. Yeah, thank you.
Mm-hmm. Yeah, we're let's see. We have I would suggest we have a couple minutes left here for questions.
Okay.
Please, any of the attendees, please feel free to put a Q&A question in the Q&A. And if you have any questions after the fact, you can put them in the Hoover app. You can, connect with Dwight Pan or other presenters there. And because I think that the presenters are going to be probably being in the app looking at other presentations, so you can hook up there. But yeah, so we'll just hold on for another minute here, Dwight Pan.
Yeah, no problem.
No other questions right this second, but let's hold on for a minute. Oh, it looks like we have a question here.
Oh, I have a question. Yeah.
Let me read it out loud.
No problem.
So, how to solve the issue of torque drop during magnetization shifting? And then Mohammed says to keep the torque continuous, to be clear. So I don't know if you could see those and respond to those. Can you speak to those questions? Again, how to solve the issue of torque drop during magnetization shifting?
Torque drop.
To keep to keep the torque continuous during magnetization shifting?
Okay. I got his question. I think he's asking that during the transition, suppose from 50% magnetization to 100% magnetization, there will be, okay. In our case, actually in our Lapierre group, we have done the offline transition of the magnetization shifting. Suppose we want to go from 50 to 100%. So we have done it offline. We provided a proper current pulse, and accordingly, measuring the terminal voltage of the VFM, variable flux machine at no load. Basically, it is running at a generator. We can quantify the magnetization level. But during the magnetization shifting, dynamically, I have not done that much research, but only I have done it offline. I think the person is asking about it continuous. Continuous, I have not done till now. I'm not sure. Later I can answer the person.
Yeah. I think we have my vet is showing me one more question that may have come in through the Hoover app. So let me read this, Dwight Pan. We'll do one. This will be maybe the final question. Okay.
Okay.
So memory machine is the type of PM machine in which we change the magnetization state of the PMs that give us a wide range of speed of motor through the change of current pulse.
Yeah.
How is the current pulse given to the machine?
Okay. to actually in the field weakening region, we reduce the magnetization level of the nuclear magnet to lower level, because as the in the high speed region the frequency increases, so we have to as the terminal voltage is constant, we have to reduce the magnetization level. So we do the magnetization and demagnetization in offline by providing a DC current. First, we clamp the shaft of the variable flux PMSM by a C clamp, and then from the available characteristics of the variable flux PMSM, what is the required current? We will apply that current, and after applying those current, we will check the back EMF of the variable flux PMSM at no load, and by seeing the magnitude of the back EMF, we can quantify, okay, this is 50% magnetization level, and this is 75% magnetization level, this is 25%. Thus we perform the test in our lab. Thank you.
All right. Dwai Pan, thank you for answering those questions. We appreciate that. And thank you for the great presentation on the variable flux machine.
One question regarding the dynamically, I didn't perform till now, but I have done offline test. But the person has asked how I can change dynamically the torque, the magnetization level. So I have not done. Maybe if you ask me, I can mail me. I have my email ID. I can know those answers and answer him.
I appreciate that.
Yeah.
I think we're going to work to close this session out, because we're going to be starting our next one shortly.
Okay.
Dwai Pan, again, I want to thank you for your time. Thanks for the excellent
you,
presentation. It's much appreciated. And so we're going to close this out. And I just wanted to just let everyone know that you can join the next session. It's starting just in a couple minutes at 2:20 Eastern Time. And it's going to be another presentation from the university on electromagnetic windings and reduced space harmonics. So that's coming up in a couple minutes. So with that, Dwai Pan, we're going to close out.
Okay. Thank you, Brad. Thank you, Kelly.
All right.
Thank you, Beth.
All right.
Thank you, the JMAG team. Thank you very much. Yeah. Bye.
Likewise.
Bye.
Bye, Dwai Pan.